buildings and FIFA.
Thank you very much for the invitation. It's really my pleasure to speak at the Newton Institute. So I'm going to try to introduce buildings first, and then certain system algebras associated to buildings. Okay, so I really apologize if I don't mention some people. I really don't want to talk too much about the history of the subject. Of course, there are many more papers on this matter, but just this kind of theory of system algebras associated to buildings was developed by Robertson and Steger. It started like in '99, and they were really working on this for more than 10 years. And actually, this is some kind of what is the philosophy of this theory, that you define certain geometric objects like higher dimensional alphabets, and then by certain rules you build up system algebras, and this kind of geometry behind allows you to define the system algebras explicitly and compute their K-theory. But then there were several instances where this construction was used. So the most recent, like Marcinic and Marcoli, defined KMS weights on higher rank buildings using this system algebras. And in this talk I will try, at least to, I hope that I get there, to talk about at least a little bit about a K-theory of system algebras independent from group actions. So what I would like to say that most of examples of system algebras of Robinson and Steger come from group actions on buildings and products of trees, but then the K-theory, it really depends on the group structure. But then what I almost accidentally discovered, that in some instances for quite large classes of algebras you can compute K-theory, and then it turns out that it depends only on the structure of the building itself. It doesn't depend on the group anymore. Okay, but okay, we have a operator algebra conference, so maybe I should start with elementary example and say what is the Kelly graph, because we will need Kelly graph. So you just take elements of a group as vertices, and then you connect two vertices in your Kelly graph if there is a generator from a group bringing one element to another. And of course, in my talk I will talk mainly about infinite groups, but okay, such an elementary example of a finite group just has 3, right? This is its Kelly graph. Okay, but the main object of my talk is buildings, and buildings were started by, the theory of buildings was started by Jacques Tietz in 50s, but it was really like a very classical algebra, and like with this setting of Tietz one needs maybe a half of a year course to talk about buildings. But just to give a definition, okay, maybe not half of a year, but at least like more than one lecture for sure. And we are really lucky that there is this geometric interpretation of buildings, and also this is what I would like to say, that a lot of results which and a lot of objects which I'm going to talk about today can be defined in a high dimensional settings as well, but I will mainly stay with the dimension 2, because it's already complicated enough if you haven't seen this subject before. So I will talk about two-dimensional Euclidean and hyperbolic buildings. So how you can think about it, you can think about it as a two-dimensional complex, which is a union of tessellated planes called apartments. And what is the chamber? It's just one polygon in this tessellation. Then for any two chambers, there is an apartment containing those chambers, and if two apartments have a non-trivial intersection, then there is a isomorphism of apartments fixing their intersection pointwise. And again, if you haven't seen buildings before, this third property just means that all apartments in the building are the same tessellations. Okay, maybe one should draw what is the tessellation. Actually, what is the good example of an apartment of a building? It's one of the Escher's pictures, and I just deleted it from my slides just not to have too much entertainment, but
that was a mistake.
but this is an example. But I think everybody can just now imagine the Escher's picture, and like you can think about those like beautiful tessellations of hyperbolic planes, but just what is it can be even much easier tessellation of Euclidean plane, right? Because I try just in the same go define Euclidean and hyperbolic building in kind of in the same time. So this is also in like infinite tessellation of an Euclidean plane by just regular squares, and it's also perfectly fine as an apartment for a building. And of course, if you just take one tessellation, you can think about it as a kind of trivial building, because of course if you just have one infinite tessellation, you pick any two chambers. So again, I just repeat, the chambers are those like polygons which you use in your tessellation. So of course if you pick any two chambers, then this unique apartment contains both of those chambers. But we are interested in something which is so-called like thick buildings. What it means that every edge is contained in at least three chambers. Okay, so that you have really uncountably many apartments in your building. Okay, so by the way, any questions so far? Because this is kind of a fundamental definition of my talk, and I would like to kind of keep as many people awake as possible. So just now maybe it's a good time to ask a question about the building. Okay, great. Yeah.
Is it possible to draw a picture of such a thing? I mean, if it's a complicated one.
So of a building, it's picture maybe not possible to draw, because two-dimensional thick building, even a building of thickness 3 cannot be embedded into a three-dimensional three-dimensional space, right? Because we have a lot of tessellated planes, and then in every edge, everywhere, there are at least of three planes are meeting. At least like there is locally, the picture is like this.
Not even in 3 dimensions.
No, it's because, as I said, that usually you say that a building is two-dimensional, it means the dimension of an apartment.
Yeah.
But to realize even two-dimensional building, one needs at least dimension 5.
Oh.
Right, but that's why, so this brings me to motivation, the question, how do we handle such objects, right?
You could draw a one-dimensional example, that might be helpful.
Okay, so one-dimensional example, yes, so one-dimensional example it's of Euclidean building. It can be just an infinite tree. So this right, so infinite tree of the same valency. You can think about chambers as being edges of the tree, and apartments, it's infinite path going from one point in infinity to another point in infinity. And then you can also check the second axiom is really easy to check, because if you have any two edges in this infinite tree, you can always find an infinite path which contains those two edges. Okay, then, yes, so thank you, it's actually a good idea. Okay, then I need a couple of more definitions. So we will say that a polyhedron, it's an object which is obtained like from several oriented polygons by gluing together edges with the same labels respecting orientations. So what I'm thinking about, we take a bunch of polygons, and then we write some words on the boundary, and then we identify the sides with the same labels respecting orientation. So actually, again, from elementary topology, you can think about a picture of a torus when we take a square write like a word AB, A inverse, B inverse on the boundary, then we identify sides with the same letters, and we get a torus. And what is good in this picture of a torus, that actually we can think about the fundamental group of the torus acting on the universal cover. And actually, for the picture of the torus, the universal cover, it's a tessellation of a Euclidean plane by equilateral, actually just by squares, where the fundamental group of the torus acts by translation, right? And you can also think about the action of a fundamental group on this tessellated plane, and then the quotient, it's exactly the torus itself. And of course it's like very elementary, and we all had this in elementary topology course. But why I wanted to remind this, because we use the same idea of constructing something finite, and then we think about we take the universal cover, and it will be my approach to buildings, that we are going to construct some like two-dimensional finite complexes, but then the buildings are their universal covers. So it's like a way to get buildings without going too much to the theory of buildings in a way. And I need one more definition. I need a definition of a link. So imagine you have your complex, and then look at a sphere of a very small radius centered in one of the vertices of your complex. And then the intersection of this sphere with the complex is a graph, because we are staying in two-dimensional case. And this graph is called a link. So now again, let's take some elementary example. So for example, we can even look at a tetrahedron. And imagine a sphere of a very small radius at a vertex of a tetrahedron, and then the intersection is just a graph with three vertices and three edges. And this is a link. But of course, the example is too easy. We are actually interested in much more complicated links. So this is, for example, a link to get the easiest building. So this is a link to get a so-called A2 tilde building. And again, the motivation is really to use the groups acting on this Euclidean A2 tilde building to construct sister algebras. So, okay, now I just would like to explain a little bit what is this and how this graph, what is the structure behind of this graph. So we can think about those xi's as points and xi inverses as lines of a so-called finite projective planes. But again, you don't need to know what is the finite projective plane. You just can think that one type of vertices is points, another lines, and then as soon as your point lies on a line, then there is an edge between those two vertices in a graph. And actually, this is another example of a one-dimensional building. It's so-called one-dimensional spherical building. And do you remember we had this properties of a building that it has to contain chambers and apartments, and then there is this property that any two chambers are contained in an apartment. So now it can be a question to the audience: what are the chambers? So yeah, of course, like clearly some people know, but so they are just edges, right? So the chambers are edges, and you can just and the apartments are cycles of length 6. And in fact, it's kind of nice and easy exercise. You can take any two chambers and you can find a 6th cycle which containing those two chambers, right? It just, of course, like I'm going very slow, but it's really good to have at least some examples in mind. Yeah, any questions? Yeah, it's 7.7 lines. Okay, and why I was talking about polyhedral links for such a long time, because actually there is this very nice result of Ballman and Breen. It's a way to get buildings by geometrical methods. So if you have a compact two-dimensional thick polyhedron such that all the links are saying generalized M-gons, maybe I don't define all those M-gons, we can just think about graph on the previous slide. So those graphs have to be one-dimensional buildings themselves. Then the universal cover of such a complex is a building. So you see here, we don't need to define really buildings algebraically. We can just have like it's really similar philosophy to this picture of a torus, that we want to get something finite and then to be sure that the links have certain shape, and then we know that the universal cover is a building. But then if we manage to construct such a polyhedron, we have an additional bonus, because the fundamental group of this polyhedron will act on a building co-compactly. Of course, if our polyhedron was finite. It's really similar to the torus. Then the fundamental group of the torus acts compactly on this tessellated plane. Okay, but then of course the life still is not that easy, because you have to have some way how to get this polyhedron. Because of course, like if you just look at a tetrahedron, it's very easy. It's, of course, it's obtained like from 4 triangles, but it's really easy to glue them together. But of course, if you want to get a link, which is like this finite projective plane, then it becomes kind of technically difficult question. And so some time ago, I had a combinatorial construction, which I called like polygonal presentation. And again, the definition is a bit long and technical, but I will just give some examples of such polygonal presentations. But what is the idea behind is to describe what are the properties of the words are needed, that if we write them on the boundary of certain polygons, then after gluings we get prescribed links. So, and kind of I showed that one can really get prescribed links if you want to get a polyhedron. Of course, I don't claim any kind of classification of this kind, because it would be really difficult and maybe even impossible. But still, it's this kind of a tool, because as I already mentioned, those polyhedra which you need to construct buildings, they cannot be embedded into a 3-dimensional space. So just to describe the faces of your polyhedron with words, and then to have your identification scheme or labeling schemes, then it really gives you the structure, and you can really keep track what is going on in your building. Okay, so just to give a flavor which kind of results I was interested in, that for example, in geometric group theory, it's difficult to get groups acting on triangular hyperbolic buildings. And with the collaborator of mine, we kind of have found all groups acting on triangular buildings with the smallest possible link. And so how those polygonal presentations look like. So this is just two of our groups. And what you do, like for example, why I say it's a group, but it's just a bunch of some words. But actually, what you do for each triangle, for each triple, you take a triangle, you write your word on the boundary of this triangle, then every letter here appears 3 times. Then you glue all of those 15 triangles together. You get a complex with 15 faces and 15 edges, and then the universal cover, it's a hyperbolic building. And actually, in this case, even there is again like Escher's picture for an for an apartment. It's called Circle 3. Okay, but it's just to give a flavor how those polygonal presentations look like. And actually, this is kind of a maybe question to the audience to discuss later, because with those particular examples, I have no idea if one can get any interesting sister algebras. But there is another good example, which is, yeah.
That was link is a K33, is it?
No, this is not K33. This is generalized quadrangle. It's a graph of girth 8 and diameter 4. So the triangles are the chambers are regular hyperbolic triangles with angles pi over 4, right? And we have like the apartments a plane tessellated by these triangles, and there are 8 of them meeting at each point, right? So just so another good example, which is really good also from the sister algebra point of view. I already started to draw it. So what we do, we start with a group with 7 generators and 7 relations, and in this case, it's really, we can already use relations for the group. So we take it's an example of a polygonal presentation as well. So we take equilateral triangles and we write each word on the boundary. So you see here the first word is x0, x1, x3, and I already started. Okay, here I draw 3 triangles, but you can imagine that the rest also you can draw 7 triangles and write those words on the boundary. And so we have a lot of those triangles. And now, even if you didn't catch the definition of a building from the first part of the talk, now you can have in mind another definition of an Euclidean building, because you can just take the Kelly graph of this group, and we had a definition of the Kelly graph in the beginning, and then as soon as you see a triangle in this Kelly graph, you fill it in with a triangle, with a 2-dimensional triangle. And this is a particular case of a building. This is, so you may check that every vertex has degree 14, 3 triangles meet at each edge, and again, any 2 triangles contained in a plane. So there are plenty of those planes. But also, how you can think about this building, if you take those 7 triangles, glue them together, glue the edges with the same labels respecting orientation, then the link will be that graph which I showed like really several slides ago. The link will be this graph, and the universal cover will be a building. Okay? I'm just saying that actually this group first appeared in the theory of small constellation in papers of Edgeworth and Howe, but then with relation to buildings, it was first it appeared in Cuntz-Krieger, Montero-Zappa papers, and this is the easiest example in so-called Cuntz-Krieger construction, but I will not talk about it much. Okay, so now we are already ready to move slowly towards sister algebras constructions. So first of all, so we have this building, and then we need to define the boundary of the building. And how we define a boundary of at least 2-dimensional Euclidean building. Now we will talk about Euclidean buildings mainly. And so we saw how the apartments look like, right? It's some planes tessellated either by squares or by triangles. And what is the sector? We just pick one corner, and then we make it infinite. So this is a sector. All right. And 2 sectors are equivalent if their intersection contains a sector. And what is the boundary of the building? It's classes of equivalences of sectors. So this is the boundary of the building. And now I need one more notion which somehow, by some reasons, never appeared in any kind of geometric group theory context, but which is important for the sister algebra constructions. It's so-called multidimensional words. Oops. Yeah, so how we can think about multidimensional words? We may use, so actually it's rectangular regions in your building, which are somehow parts of apartments, decorated by the group action. Because, of course, if you have just a torus, it's kind of a trivial example. Everywhere in the universal cover, we can have this decoration with A and B, which are generators of the fundamental group of a torus. But saying we have something more interesting, saying we talk about this group on the previous slide. So how this building looks like, we already know that it's a universal cover of a complex which consists of triangles. And how the two-dimensional words look like, that we pick some region in a building, but then we remember that we have a group action on this building, so actually all the edges of the building are decorated with the generators of the group, whatever, right? So we have all the decoration in your rectangular region, and this is your multidimensional word. Okay, so the alphabet for multidimensional word, it's not just generators of a group, it's either relation of a group, like in this case, or if now we remember about the polygonal construction which I was talking about, that actually we are given a set of polygons with certain words on the boundary, and then we glue them together to get a polyhedron. But then we can take the universal cover of this polyhedron and look at the rectangular regions tessellated by the faces of the polyhedron. And since we had some labelings on the sides of the polyhedron, then it will be inherited in the universal cover, right? So this case is even quite easy because we have only one orbit of the group action, so it means that our polyhedron had only one vertex, which makes life easier. But in fact, this definition, like of multidimensional words, it looks for any polyhedron with any number of faces. And what, of course, I haven't written anything about it yet, but I think that also we can have just multidimensional words, even if our buildings are not locally finite. But it was just kind of a small remark for specialists. And yeah.
Question: does this include words?
Yeah. It includes words, because actually what is my next step is to go back to Cuntz-Krieger algebras, which to a standard construction of a Cuntz-Krieger algebra, which comes from action of a free group on a tree. So of course it's in the dimension 1, it's just words. Yeah, you're absolutely right. And yeah, so now what is another important remark? It's how do we define products of such multidimensional words? Because of course for usual words you just put them next to next to each other, and this is your product. But then how do we define products of multidimensional words? And so let's take another color. So maybe now this, we don't need those letters. So imagine your tessellated apartment. We take one word, and then, so as I said, that the words are two-dimensional rectangular regions, they don't need to be square. And now for a product of words to exist, we need that the so-called like final tile of the first word coincides with the initial tile of the second word. I think this is your second word, right? But then the question is the following. Fine, we have those two words such that the final tile of the first word coincides with the initial tile of another word, but it's not a rectangular region, right? It doesn't look like a word. But now what we do now, this is the point when we do use properties of the buildings and properties of the groups acting on the building, that what happens that we can, there is a unique way to finish the picture. So so here everywhere there are decorations coming from your polyhedral of your group actions on buildings. So there is a unique way how we continue this picture that it becomes a rectangular region. Okay. So any questions about this product of words, because this is important for the sister algebra construction. So okay, this is like objects. Which do we need? First of all, we need a boundary as classes of equivalence of sectors, and then we need the products of multidimensional words. Okay. So, but now let's make life a bit easier and just, it's not clear how to use chalk and okay, so now just very briefly let me remind you Cuntz-Krieger algebra construction, which of course like operator algebra people know it much better than me, but then I just want to generalize certain things for the higher dimensions. And we start with the free group with two generators. Then what is the Cayley graph? The Cayley graph is this four-valent regular graph, right? And then, yeah, the vertices we can treat as, or we can even think about words on this Cayley graph. And what is the boundary? The boundary of the tree, it's semi-infinite words. Then it's there is a natural topology which is defined on this boundary, and I think it's really kind of a classical construction which I would like to remind. And you see what is the difference, that in a one-dimensional case it's easy to define the boundary. The boundary, it's just those semi-infinite words, and yeah, and it's just with given prefix and so on. So I think maybe this is really quite classical construction, which I don't need to kind of talk too much about it. And then, so saying you have this free group acting on a tree, you have the boundary of the tree, and then you have this naturally defined cross-product algebra of the continuous functions of the boundary of the tree and the group action. Right? And then just working a little bit, you get this kind of standard Cuntz-Krieger relations. Okay, but also what I would like to say, how I think about it and how to kind of relate it to buildings. In fact, the partial isometries of them in the Cuntz-Krieger algebra, you can define as partial isometry between finite words having the final element, such that the final elements coincide, right? So you can actually look at the words in this graph, and you say that two words are the same if their final tile is the same. No, not the same, but if there is a partial isometry between two words, if their final tile is the same. So I don't know if this is that well known in the sister algebra community, that those partial isometries of them you can define as partial isometries of finite words having the same final tile. Okay, and now this is also like behind this Cuntz-Krieger algebra, there is this transition matrix which tells you where you are allowed to go in the Kelly graph of the free group, but it's also very easy, especially for the geometric group series, that what zero means that you don't have reduced words in your path, right? So you're not allowed to, if you are at A, you cannot take A minus 1 after it, but everything else is allowed. So this is your transition matrix for this picture of a free group on two generators. Okay, and now we can just remind the general definition of the one-dimensional Cuntz-Krieger algebra, right? That actually I think it's one of the definitions where you do need this transition matrix. So you can think about this matrix as the matrix of a previous slide, right? So, okay, so now I think that we are ready to go to the higher dimensional Cuntz-Krieger algebras, right? So, okay, now let's again look once more at this picture. We have a group action, so in this case on a Kelly graph, and then we look at the boundary, and then we look at this cross product algebra of the continuous function of the boundary of the group, and then we have this Cuntz-Krieger algebra, which is defined by partial isometries between words with the same final letters. And here in the one-dimensional construction, our generators of the group in the cross-product algebra and our kind of elements of the words are the same. It's generators of the free group A and B. But now, when we go to the higher dimensional case, what happens that, first of all, instead of trees, we consider buildings. And we consider groups, instead of like saying free group in the Cuntz-Krieger construction, we consider those groups acting co-compactly on buildings, which I was talking about during the first half of my talk. And again, the boundary of the building is defined by classes of equivalences of sectors. And yeah, so again, we think about two-dimensional case. Let's think about groups which are, so there is one more element, like to be able to use some of the results of Cartwright and Steger. We can, some of their results ask for so-called type rotating automorphisms. So I can briefly explain what is the type saying in two-dimensional case. If you have your Euclidean planes tessellated by triangles as apartments, then all the vertices of your apartment you can just tessellate, you can just mark with numbers 0, 1, 2 in a consistent way. So those are types. And for certain results for cyst algebras, you need to rotate those types by the group action. But of course, this group, this kind of example, which I have in my talk, it's really type rotating action. Okay, and then there is this cross product algebra, and it is isomorphic to an higher rank Cuntz-Krieger algebra, which is associated with two transition matrices. And these transition matrices can be obtained just by looking how your triangles behave in the building. So for the size of the matrices, it's the size of triangles multiplied by 3, because every triangle comes with a marked vertex. But then how you say that in your matrix, in your transition matrix, one element is coming from another, that if in the picture of apartments you can get one triangle from another just by one step. So you see that here this picture which we had in the case of graphs becomes more complicated, because for graphs it was very easy to say this about this compatibility condition. You just say that we can write A after B if A and B are not inverse, right? So the only thing which was forbidden in a one-dimensional case, it's A inverse next to each other. But in the building, we have to have certain configurations. So now our elements of the alphabet are triangles. But then when we can put two triangles one after another, then if in some way in the building you can find such a configuration that the triangle in between also exists, right? So like, of course, it's always nice to have more explicit examples, but the easiest example, which comes from the smallest group with 7 generators and 7 relations, it's matrices 21, 21, right? So it's kind of no use. Imagine here I would write a 21, 21 matrix. It doesn't help. It just, one tries to explain that there are some rules behind which come from the group action. Yeah, but any case, I would like to summarize what I was talking till now. So what was the framework of Robertson and Steger? It's to define certain multi-dimensional alphabets where they really have no restriction on dimension, and then certain compatibility conditions. Again, to write down those compatibility conditions, it's maybe at least 1 hour just to read those compatibility conditions. But nevertheless, they are kind of, when you start to work in this business, you see that all those compatibility conditions are really very reasonable. And so this is kind of general construction which they have had in their paper in Crelli in 1999. But then the problem was that actually it was not that many known examples of also not that many sources to find such multidimensional alphabets. And their main source was this paper which I already mentioned of Cartwright, Steger, Mantora-Zappa, where there were examples of two-dimensional groups acting like on two-dimensional buildings, and they had only one orbit, right? So in the context which I was talking today, it means that they were looking at polyhedra with one vertex, all triangular Euclidean faces, and links which are incidence graphs of finite projective planes. And so, but then it turned out when I understood this paper of Robertson and Steger, I realized that a lot of polyhedra which I was constructing, they just fit into this Robertson-Steger construction just on the nose. It's really just of course every time you have to check those combinatorial conditions. And this is what I wanted to, that's why I kind of called them polygonal algebra for the two-dimensional case, because we have this kind of polygonal construction, polygonal presentation, and then you use the words from there to define your algebras. But then of course it can work for any dimension. We can get such polyhedra for multi-dimensions. But okay, now we just said that okay, we have this alphabet, but I think that now we are ready to define this higher rank Cuntz-Krieger algebra. And so this is a formal definition, but how to think about it elementary, that we have this alphabet, we have multidimensional words, and how do we define our partial isometries? So the partial isometries are defined, we say that there is a partial isometry between two-dimensional words if their final tiles are the same. Okay? So with words, with usual words on the Kelly graph of a free group, we were just saying that we say that there is a partial isometry between two words if their last letters are the same. But here, we say that their final tiles are the same. And also you can think about any dimension. We think about kind of final tile, saying for cube complexes, you can also think about this final tiles and so on. So this T means final tile, and source the initial tile, and T final tile. Okay, so then just briefly mention what I was doing. As I mentioned, that I realized that actually there are a lot of examples of sister algebras which don't come from those standard examples which Robertson and Steger constructed. But then the question, what to do with them? And what happened that using this kind of combinatorial interpretations of sister algebras, Cartwright and Robertson and Steger were computing their K-theory quite explicitly. So you can compute K-theory of these Cuntz-Krieger, higher rank Cuntz-Krieger algebras using the tiles. As I said, that there are certain compatibility conditions coming from the structure of the buildings, and those conditions can be used to compute the K-theory explicitly. But then, apparently, sometimes, so like Robertson and Steger had a lot of results of K-theory computation, but sometimes it was really like computer assisted, because of course it becomes very, very messy, all those computations. But then by some mysterious reasons, sometimes it turns out that your k-theoretical results don't depend on the structure of the group anymore. It depends only on a building. So with a young mathematician from Chicago, we have, for example, a result like this, that the order of the class of the identity of this cross-product algebra is actually q minus 1 when q is 2 to the power l minus 1. So what is the q actually behind every building? Do you remember I was, like in the dimension 2, I was saying that every triangle is contained, every edge is contained in several triangles. So there is a parameter q, which is a prime power, and the number of the triangle meeting in the same edge, it's actually q plus 1. And by some mysterious reasons, the order of the identity in k naught in those two-dimensional Cuntz-Krieger algebras is q minus 1. Okay, we didn't go through all the q's because it becomes technical, and we were actually just looking at 3 orbits, because I think it works for any number of orbits, but like it's really kind of technical. I wanted to show the flavor of the results, and just for me it's interesting. Maybe it can be used somewhere, this kind of Cuntz-Krieger sister algebras and so on. Okay, thank you very much for your attention.
Thank you for this nice talk. Any questions?
You know if the C-star algebras that you're looking at are related back to like p-adic representations, admissible representations?
I don't know. Actually, I don't know if they are related, because of course it can be, at least in some algebras, it can be some kind of natural representations, because what I didn't mention, there is a whole class of buildings which come from like PGL and QP, and the groups I was talking about, they have like really very nice faithful representations, but I don't know if they are related to the representations of algebras, because it's really interesting question, because what also I didn't mention, even with much easy invariance, like saying abelianization of a group, clearly there is some connection with the case theory, because but this is just evidence from the computer search. If you look at kind of evidence for almost 100 of groups, that if you look at the primes which appear in the torsion part of case theory and primes which appear in the abelianization, it's actually the same prime. The only difference is the primes which appear in the order of the identity, because first I thought, very strange, what are those numbers? But then I realized that it's really the order of the identity which also plays some role in the case theory. But otherwise, clearly there is some relation between the abelianization and case theory. But of course, it's a very interesting question. We can discuss it later.
So the classical Cuntz-Krieger algebras, they come with this canonical extension, right? There's an extended one, and then there are quotients of that extension, so forth. Is there a similar picture here? And
actually, I don't know. But what kind of extension do we mean? So let's come back to the classical version, right? So this is what I thought. I just kind of I was just looking like very classical paper of 1980 of Cuntz-Krieger, right? And then you have this you can interpret it as a action on a Kelly graph of a free group.
Yeah, but what I mean is that It's like Kuntz algebras themselves. They're quotients of.
Ah, okay, but there are different things. Kuntz algebra is something else, and the Cuntz-Krieger algebra, it's this kind of more,
There's a more general thing, which is you start with, Hilbert bimodule and so forth, and you can construct a kind of an algebra, and then there's a quotient of it, which is the Cuntz-Krieger algebra. I mean, this is a very general construction of Pimsner, much later on. And I was just curious.
Interesting. No, I don't know that. I don't think that.
That is the quick way to compute the K-theory, for example, for such algebras, to just write down this exact sequence, and then it should be quite a lot of data about the discrete.
Yeah, but now we are coming to another question. What do we mean by computing K-theory, right? Because of course, like people from K-theory sometimes, like you say, there is a exact sequence like this and like this, so the K-theory is computed. But in this, like when you describe your sister algebras in this like very, very explicit combinatorial way, you can say that, okay, the K-theory of such and such group, it's saying z to the power n, it's a torsion-free part, and the torsion part, it's like a direct product of a cyclic group of order 2 and cyclic group of order 3. So this is what I mean by computing K-theory. It's really to get very precise groups using such combinatorial construction. But we can discuss later. It's very interesting to see if there is this kind of generalization in more abstract way.
Is the boundary you talk about the same as the one that Borel and Serre, say you did it for PGL3Q2?
Yeah, sure.
It's the spherical building.
Yeah, it's isomorphic. It's of course in this spherical building in infinity. Yeah.
Any more questions? Not, thanks, Alina, again.